Welcome everybody to another episode of Back to Basics. This week we're going to be talking about Schottky diodes. Now, when I did my original video on how diodes are constructed, I very obliquely referenced a couple of different versions of diodes. Most notably, we've got light-emitting diodes, we've got Schottky diodes, and we've got Zener diodes. Those are the main ones that I'll talk about. I may pick some more obscure ones to talk about just for fun. But I'm picking Schottky diodes for this week because I'm going to be playing with some Schottky diodes in some upcoming videos, so I thought I'd do a basics video on them. So a Schottky diode is named after the German physicist Walter H. Schottky. They're also known as Schottky barrier diodes or hot carrier diodes. They're built a little bit differently from your normal diode. They don't have any p-type semiconductor material in them. They just have a metal lead and some n-type semiconductor material. So let me sketch out real quick the basic idea of what a Schottky diode looks like inside. So you're going to have the cathode coming in here, so we'll say that's the minus, and it'll have a metal plate, and then you'll have a section of very heavily doped N-type semiconductor material, also notated as N+. And I'll talk a little bit more about this in relation to regular diodes. It's something I left out kind of intentionally in that video, but we'll touch on that again here in just a moment. So then you have that heavily doped N+ material, and then you have a section of your standard light doping N-type semiconductor material, and then at the top you have the anode. And around that anode is going to be a sort of a screen, they call it, or protective barrier of silicon dioxide or some other non-conductive material. And the reason for this is because this little plate of metal that's fused onto that N-type semiconductor material, out of necessity, they're going to have very sharp edges. And at those edges, you can actually get an EM field developing. So to prevent that from happening, they put a ring of non-conductive material around it. Now, the reason these are built like this is because if you put a piece of metal against lightly doped N-type or P-type semiconductor material, you will actually get, what color should I use for this? I guess I'll use black again. You'll get a slight depletion layer that develops between the metal and the semiconductor material. To prevent this from happening, you'll actually put a section of very heavily doped material against the electrode that's being attached to the semiconductor material. And that's what they actually do in regular diodes. When I drew the example of a standard diode, let's just do it here. So I said they have the P-type material, and then they have the N-type material, and then they attach the electrodes to either end. But in reality, they actually have at the ends of each of the diode a section, and I'll just draw it thicker here, a section of heavily doped P or N-type material, like that, and then they have the electrodes. And this is to prevent a depletion layer from forming where the electrode bonds onto the semiconductor material. But we want that to happen with a Schottky diode, because we still need that depletion layer. So we allow it to form between the metal of the electrode and the semiconductor material. And then we just heavily dope the other end so that there's no depletion layer at the cathode. The cathode. So why do we want to do this? Well, there are two main reasons why we would want a Schottky diode. The first is that it has a very low forward voltage rating. Typically, the forward voltage is between 150 to 450 millivolts. So much, less than half that, almost, of a standard diode, which has a forward voltage of 6 to 700. Although I've noticed a lot of diodes nowadays have, just standard silicon diodes have a forward voltage of about 0.5 volts, 500 millivolts. And the other really good thing about Schottky diodes is that they have a very fast recovery time when reverse biased. So you can use a Schottky diode to rectify very, very high frequency signals, anywhere from, I think it goes up somewhere into the gigahertz range. Let me just confirm that. I have my notes here in front of me. Where did I have that? Yeah, so a standard Schottky diode will function between 200 kilohertz to 2 megahertz. And they also have a special type of Schottky diode called a small area Schottky diode, and they often operate at frequencies up to 50 gigahertz. So they can recover very quickly and start conducting in forward bias after being reversed biased with a an AC signal, an alternating current signal, or radio frequency or audio frequencies, or whatever happens to need to be rectified. So just for fun real quick, I'm going to grab my little diode tester thingamabob here, and we'll grab one of our bog standard 1N4007 diodes here, and we'll go ahead and clip it in, and let's go ahead and see what it says about our forward voltage. So testing. So it says 703 millivolts, and the capacitance reading on it is corrupted. I think the processor in this is going bad. I need to buy a new one. But we don't really need to know what the parasitic capacitance is on this diode. The important part is this 703 millivolt rating, or reading, rather. So let's go ahead and see what the Schottky diode has to say. So we'll grab one of these Schottky diodes. If anybody's curious, this particular one is a 1N5819 1N5189 Schottky diode. It's got a forward PIV of 40 volts. That's something that I forgot to mention. Schottky diodes have a much lower reverse peak inverse voltage rating on them, whereas these 1N4007s, they can take a peak inverse voltage of 1,000 volts before breaking down. Schottky diodes can only take, well, these ones, which are the highest voltage ones I could find for cheap, these ones will only take 40 volts, but anywhere between 16 and 25 is standard for a Schottky diode. So let's see what this one says for its forward voltage. So it says 256 millivolts with a leakage current of 3 microamps. That's something we should also show you. So that has a leakage current of 3 microamps. And this guy has a leakage current of 2 nanoamps. And that's another disadvantage of Schottky diodes. When reverse biased, they have a much higher leakage current than a standard silicon diode. And this has to do with the fact that there's no P-type semiconductor material to sort of inhibit that reverse biased leakage current or voltage rating. So anyway, I think that pretty much covers Schottky diodes. If I left anything out or or made anything unclear, feel free to ask me any questions in the comments below. If you haven't already, consider clicking here to subscribe. Right over here will be a video that YouTube thinks you'll find interesting based on your own watching habits. Right over here will be the Back to Basics playlist, and right here will be a link to my Patreon, which you can get access to these Back to Basics videos 1 week in advance if you sign up, and you can also help support the channel. So thanks again for watching, and we'll see you next week. Bye-bye.